Greetings. So, we have begun to get some sort of a handle on the many electron systems, and we dealt with the wave function for a pair of electrons as the smallest many electron system, just the 2 electrons, and we understood the difference between the singlet and the triplet state, how the pairing takes place, parallel or anti-parallel, and all this was aimed at obtaining the expectation value of the single particle and the 2 particle part of the Hamiltonian, so that we can get an expectation value for the many electron Hamiltonian in a Slater determinantal wave function, and subsequently use variational calculus to get a minimum of this expectation value, subject to constraints of the individual spin orbitals being normalized and orthogonal to each other. So, those are the constraints that we have in mind. So, the expectation value of the 1 electron Hamiltonian turns out to have a very simple form, and that is what you have over here, which we obtained in our previous class. And this integration becomes easy because this is a dummy label, so it really does not matter what you put over there, but Q stands for 4 variables. There are 3 continuous variables, the space variables, and there is a discrete spin variables. So, the integration includes the summation over the spin coordinates. So, let us have a look at this integral. This is integral over Q, which stands for all the 4 coordinates, and this is a triple integral over the 3 space variables and a summation over the spin coordinate. That is what it means, right. So, let us use this and write this explicitly in terms of the space integrals and the spin summation. So, this is what you get the triple volume integral over the volume element dV, then you have got u alpha I star, and the argument now is r, which is the space coordinate. So, it is this operator. Now, this operator does nothing to the spins, okay. We know precisely what that operator is. It is just the kinetic energy and the potential energy operator for every single electron. So, it is not going to touch the spin, and therefore, the summation over the spin functions can be carried out separately, and this summation is summation over zeta alpha I complex conjugate, because this is coming from this complex conjugate part, and then you have a spin function from this state, right. So, this is the summation over the spin part, which can be carried out separately, and notice that when you take into account this complex conjugate term, so the complex conjugate of zeta alpha I is alpha I zeta, right. So, you immediately recognize that this is nothing but the resolution of unity. So, this is just, it gives you just a factor of 1 multiplication, and the summation over spin can be carried out separately, and this integral, which is the expectation value of the 1 electron Hamiltonian, becomes very simple, and all you get is this summation over I going from 1 through n, but this integral is now only the space integral, because the summation over the spin part gives you a multiplicative factor of unity. So, it is a very simple space integral, it is a triple integral over the r theta phi or x y z or whatever be the 3 space coordinates you are using. Now, we are ready to handle the 2 electron Hamiltonian, and this will be handled in pretty much the same way, and you already have the tools with you. So, I will not work out the micro steps in between, that is something that you can do for yourself, but the general machinery is exactly the same. I will certainly take you through the main steps which are involved, and this is the general expression for an arbitrary operator which is symmetric under permutations of the particles, and we found that here you have factorial n terms in this part and another factorial n terms in psi star when you integrate, right, of which you have, through the trick that we discussed in our previous class, you only need to consider the product of the diagonal elements on this side, and on this side you certainly have the psi star, and then you have a multiplicative factor of root of factorial n, and you remember how we got it, right. And since this expression is valid for any operator which is symmetric with respect to permutations of the electrons, we had used it in our previous class for H1, and today we will use it for H2, which is this operator, which is a 1 over Rij operator summed over I and j, j not equal to I, right, and you want to count every interaction between a pair only once. So, there is a factor of half. So, you count all the Coulomb pair interactions, right. So, this is your operator H2. Now, let us see if we can simplify this. We had gained a lot of simplification with respect to the Hamiltonian H1, right, the 1 electron Hamiltonian, and a similar simplification using exactly the same kind of logic and the same innovative tricks you can use to simplify this as well. Of course, it will not be as simple as it was for H1, for the simple reason that now you are dealing with a pair of electrons, but it will be simple enough. So, let us have a look at this. So, this has the psi star over here, which has got these factorial n terms, right, and we will now handle these factorial n terms the same way as we did for the H1. Okay. So, you have got all the factorial n terms sitting in this psi star. Okay. This is just the product of the diagonal elements. This is the 2 electron operator, 2 electron Hamiltonian. You have got the root factorial n term outside the integration, right, and these are the factorial n terms. Where are they coming from? They are coming from the factorial n permutations, and what we are going to do is to first get rid of this root factorial n in the denominator and the numerator. You can just cancel them out, so that makes it a little simple, right, and then the next thing we will do is handle these factorial n permutations by separating the identity permutation, the term for the identity permutation, then one interchange, and then the remaining factorial n minus 2 terms. So, in the factorial n permutations you include the identity, then there is one interchange, and then more than one interchange. So, I will deal with these three separately. So, the first term corresponding to identity is just this, what you find in this beautiful bracket. This is the product of the diagonal elements of the complex conjugated Slater determinant. So, that is what comes over here, that is the one corresponding to identity. Then there is one term corresponding to one interchange, and since there is one interchange there is a minus sign here, and the arguments q1 and q2 are swapped in these two, u alpha 1 star q2, u alpha 2 star q1. Okay. The arguments q1 and q2 are swapped, but the arguments of all the other spin orbitals, they remain exactly the same, they are not touched, because there is only one interchange that we are talking about. So, this is the term which appears here with this minus sign, which corresponds to a single interchange, and then there are factorial n minus 2 terms. So, you sum over all the permutations p going from 1 to factorial n minus 2, and all of these remaining permutations are stacked together in this term written over here. Okay. Now, this is going to make life very simple for us, because you can write these terms, the term corresponding to identity, then the term corresponding to one interchange, and all these remaining terms you put together in what we will refer to as a remainder. Okay. The good thing is that this remainder vanishes. Okay, and there are so many terms over there, most of the terms factorial n minus 2. Okay. So, out of the factorial n terms you need to really work with only 2 terms, all the remaining terms vanish. And why would they vanish? We did not use any extraordinary mathematics or quantum mechanics to show how the remainder went to 0 when we discussed a similar idea in our previous class. It was simply based on the orthogonality of the 1 electron spin orbitals, right. So, I am not going to work out those detailed steps because we have already done it once, and you do precisely the same thing and show that this remainder goes to 0. Okay. So, now we have to work with the first 2 terms, the term coming from the identity and the term coming from 1 interchange. Now, here again I will let you do the simplification because the integrations over q1 q2 can be carried out separately, right. These are independent degrees of freedom, and then the integrations over other variables will give you the normalization integrals which are a factor of 1. So, they will multiply out and you will be left with very simple integrals which are integrations over just 2 variables qi and qj corresponding to the 1 over rij term, and then you have this sum over I and j, half of that, and then you have this double integration over qi and qj coming from this identity and a similar double integration with a minus sign because there is a 1 interchange here. So, that minus sign has been written here in between these 2 terms. So, with this minus sign you have a similar term, and this is the one corresponding to the exchange because there is 1 interchange which is involved, right. Of course, you do remember that every integration over q is a triple integration over space variables and is a discrete sum over the space over the spin coordinate, right. So, that is it. So, now you have got these 2 double integrals to work with, and these you immediately recognize are the Coulomb and the exchange integrals, okay, which I have now written in the Dirac notation, but they are just these integrals. In the explicit, as integrals they are already written over here, and this is a brief notation. G stands for the 1 over distance operator. So, this is nothing but the difference between Coulomb and exchange. The Coulomb and exchange integrals we discussed quite extensively in the previous class. So, we know precisely what they are, right. Now, you can write the Coulomb integral as Jij and exchange as Kji. This is just a matter of notation. I would like to ask if you need to worry about j not equal to I, because when you wrote this operator you were careful that you exclude the j equal to I term, right. In the now over here in the last step I have not taken any care of excluding j equal to I, because the Coulomb and the exchange cancel for j equal to I anyway. So, it really does not matter, okay. So, that is not an issue. So, now we have got both the expectation value of the 1 electron Hamiltonian and the 2 electron Hamiltonian. The 2 together give you the total many electron Hamiltonian, and the first one is just a summation over these single particle integrals. These are summations over 2 particle integrals. One is the Coulomb, this is Ij Gij, and this is the exchange which is Ij Ji. Okay. So, keep track of the notation, this is the exchange integral, right. So, these are the 2 that you have got, and when you put both of them together and develop an expression for the average value of the Hamiltonian itself, it is just the sum of this piece and this piece. Now, what is our problem? That we should seek an extremum of this value subject to constraints, okay, and we will do that using the method of variational multipliers. But you will see that the terms really become extremely simple to handle, because the Coulomb integral, which I have written explicitly over here, contains space integrals. These are space integrals over space volume elements dV1 and dV2, and they include the summation indices, right, and this is a double sum over zeta 1 and zeta 2, because once zeta 1 comes from q1 and zeta 2 comes from q2. Okay. They both have got the space variable and the spin variable both. So, there is a double summation over the spin functions. Okay. The 1 over distance does nothing to the spin function. So, this summation can be carried out separately. So, now if you just look at this, this is complex conjugate, you have got an asterisk here and an asterisk here. So, you take the mirror image of this to get the complex conjugation. So, this is it, this is what you have got, right. So, this is just the complex conjugation as we need, and if you look at these complex conjugated terms and then carry out the summations over zeta 1 and zeta 2 separately, because these are the two terms which have got zeta 1, the other two have got zeta 2. So, you can carry out the summation over zeta 1 separately and the summation over zeta 2 separately. What do you get? You get 1 into 1. Okay. So, that is done. So, now you are left with only the space integrals coming under the Coulomb integration. Okay. This is the Coulomb integral, and this gives you a factor of unity. You have 1 into 1, and this will give you unity, and that will give you a relatively simple expression for the Coulomb integral. So, see what you started out with, and you are really getting rather simple expressions. When you write a program to calculate this, it does turn out to be quite complicated, but that is a different story. Okay, that is at a different level, and some of you will do that. So, this the spin part is now taken care of. Now, let us see how we do it for the exchange term. Here again, this is integration over the space variables and summation over the spin variable. So, you can separate the summation over the spin separately, and now you have summation coming from zeta 1 and zeta 2 coming from q1 and q2 respectively, and corresponding to these complex conjugated terms in these two terms you get these two, and you can take their complex conjugation, separate the summations over zeta 1 and zeta 2 as we did earlier, right, and what is it going to give you? So, you have got these complex conjugate terms, and you can see from this space integrals, if one of these functions is 0 where other is not, okay, because the product u alpha 1 r 1 u alpha I r 1 u alpha j r 2 is appearing in the integrand, right. So, if one of them is 0 where the other is not, it will make a 0 contribution, right. So, for the exchange contribution to be significant, there must be an overlap between the two states. If there is no overlap, this whole integral will vanish. Okay. So, that overlap is essential, which means that exchange effects do not exist between spin orbitals if their space parts do not have any overlap. So, that is very easy to see, and now we can separate the summation over the spin variables. So, this is the summation over spin variables, you have got the complex conjugate terms. So, let us first handle that. So, this is the complex conjugate of the first term, this is the complex conjugate of the second term, these two terms appear as they are, and now you carry out the summation over zeta 1 and zeta 2 separately. So, zeta 1 is already here, and if you carry out the summation over zeta 1, what do you see emerging? This is MSJ MSI. So, that will give you the Kronecker delta MSI MSJ, right. So, it will give you a Kronecker delta MSI MSJ, and then you will be left with a summation over zeta 2 with MSI here and an MSJ here. So, that will again give you a Kronecker delta MSI MSJ, right. So, that is what you get. So, you get from the summations over the spin variables, you get a Kronecker delta, which means that you have to take into account this term only when the spins are parallel, right. So, this is the delta MSI MSJ. So, if both the spins are parallel, so and then the rest of it is just this space integration. So, we get a huge amount of simplification by separating the summations over the spin variables. So, these are the integrals to be determined. These are this is the space integral, they are all now the space integrals. All the spin summations are have been taken into account. You get a factor of unity here, a factor of unity here, and a Kronecker delta over here in the exchange term. So, you have got the single particle integrals, the 2 particle Coulomb integrals, and the 2 particle exchange integrals only for parallel spins, and this is the term which will come with a minus sign because it is coming from one interchange. So, you have got a rather simple expression that can be interpreted rather easily, and now what we are going to do is to carry out a variation, minimize this, right. We want to get an extremum. So, we want to get an extremum of this state subject to certain constraints. So, the variation in this expectation value of the Hamiltonian must vanish, that is the criterion of having an extremum, and then the constraints to work with is the normalization integral for each state and the orthogonality of each state, but mind you there are complex conjugates. So, you have to maintain alpha j alpha I equal to 0 and also alpha I alpha j equal to 0, because when you are carrying out the variation it is possible to carry out the variation in the real part and the imaginary part separately, right. So, your constraints must include all of these relations. So, this is now a problem in variational calculus, okay, something that you would have done in your undergraduate mathematics course. How do you do that? Let us take just a function of 2 variables, okay, just to illustrate the methodology. I will take a function of 2 variables. You seek an extremum in the value of this function subject to certain constraints, and the constraint is expressed by this function g x comma y is equal to k, right. So, this is precisely what our problem really boils down to, that you want to find an extremum of a certain function subject to known expressions of constraints. So, if this is an extremum, the differential of f would vanish, right, at the extremum, which means that df is the partial derivative of f with respect to x times the increment in x plus the derivative of f with respect to y times the increment in y, and this would vanish. And if this is to vanish for arbitrary increments delta x and delta y, then the corresponding coefficients must go to 0. This is our normal interpretation of an extremum, but only if no constraints are present. If constraints are present, then of course you have an additional feature, namely that your expression for constraint is g x comma y is equal to a certain constant k. So, the increment in g would vanish, right, and the increment in g, which is del g by del x dx plus del g by del y dy, this is also equal to 0, and you have got these 2 relations holding good, which means that their ratios of the corresponding increments must be equal, and they are equal to each other and equal to something which does not depend on x or y, it is a constant. What is it? It is an unknown of the problem right now. This is why it is called as Lagrange's method of variational multipliers, the unknown multipliers, and they do acquire some physical meaning depending on other details of the problem. So, that is something that will also emerge from our analysis. So, this is the relationship that you get, and this is the Lagrange's variational multiplier, because what it amounts to from these equations you can immediately see that the del f by del x minus lambda times del g by del x will be equal to 0, and this the corresponding derivatives with respect to y will also go to 0, and these are precisely the conditions you will get if you were to seek an extremum of f minus lambda times g. Okay. If you had a function which is not f nor g, but f minus lambda g, what is lambda? It is the undetermined multiplier. If you were to seek an extremum of this function, it is very easy to see, we will do it. You have this f minus lambda g function, and the condition for the extremum of this function is that a variation in this function must vanish, and a variation in this function will be del f by del x minus lambda del g by del x times the increment delta x, right. And if this is to vanish for arbitrary increments delta x and delta y, then the condition that you get is precisely this, that del f by del x minus lambda del g by del x must vanish, which is what we had over here, right. Del f by del x minus lambda del g by del x equal to 0, and del f by del y minus lambda del g by del y equal to 0. So, this is what we get. This is how you obtain the extremum of a function of many variables subject to certain constraints which connect the variables. So, x and y are connected in some way, and the connection we know in our context is that these individual functions must be normalized and remain orthogonal to each other. So, this one can change, this one can also change, but their integral, the orthogonality integral between the two must vanish. You cannot change it arbitrarily without affecting the orthogonality, that is the constraint. So, that really is going to make our analysis very simple, because this is what we have got, that we have to get the condition that the expectation value of the Hamiltonian must vanish subject to the constraints of normalization and orthogonality. So, there will be undetermined multipliers for the normalization integral, which is this integral over space ui star r ui r, right. So, this is the normalization integral, this is the corresponding Lagrange multiplier, this is the undetermined multiplier, this has got the index I. So, this is lambda I, both of these indices are I, and you must have similar constraint for every single of the n spin orbitals. Okay. So, I going from 1 through n, this is what takes care of the normalization constraint, and then there is a constraint corresponding to orthogonality of ui with uj, right, the orthogonality of ui with uj and that of uj with ui. So, these are the two complex conjugate integrals corresponding to orthogonality which I mentioned earlier, right. So, these are the two complex conjugate terms, they will have variational multipliers lambda for every pair I and j. So, you have lambda ij over here and lambda ji over here, okay. But this orthogonality we are seeking in the context of the space part of the wave functions, because so far as the spin parts are concerned, we already know that there is no scope for varying the spin part, because one is going to be up and the other is going to be down. There is nothing else that you can do with it. Okay. So, this orthogonality must be guaranteed by the space part for parallel spins. So, there is a delta MSI MSJ term here, you get it. Okay. This is what will guarantee that the orthogonality is coming from the space part, and you introduce these Lagrange multipliers lambda ij and lambda ji. So, now you have plenty of these undetermined multipliers. Okay. You have got lambda ij, lambda ji, I and j going from 1 through n, but then there will be some simplification that will emerge, because if you look at the symmetry of these two equations, this is complex conjugate of this. So, there is a complex conjugation involved and there is a transposition of the indices which is involved. So, what do you get for the lambda matrix? It has to be Hermitian, right, because there is a complex conjugation and transposition. So, you have some information about lambda to begin with. You can safely conclude that it must be a Hermitian matrix, because lambda ij must be equal to lambda ji complex conjugate. So, lambda is a Hermitian matrix, and at an appropriate stage, if and when it will be useful, as will turn out to be so, we can even diagonalize it so that we will have fewer elements, but that is for later. But you can anticipate further simplification already. Okay. So, now let us make a certain approximation that you are going to vary one orbital at a time. Each orbital can be changed, but our method will make use of one orbital at a time. Now, this is obviously an approximation. It cannot represent an exact many electron system, because if you are varying one orbital, what are you doing physically? Because whatever you do in mathematics is simulating a certain physical process. Okay. There is an intimate connection between quantum mechanics and laws of nature. So, whatever quantum mechanics you do, whatever mathematics you do in your quantum mechanical scheme corresponds to a certain physical process that you are trying to interpret, and a variation in one electron orbital means that you are changing the probability amplitude. So, the probability amplitude has got a certain profile. If this is your radial amplitude axis and you are plotting this as a function of r, and you have got some profile of this kind, right, it does not matter what it is. This is what you are changing. Instead of this, it will go like this, right, you are changing this. Now, when you change this, you change the probability amplitude, you change the probability density, multiplied by charge, you change the charge density, and you are really changing the charge configuration of the many electron system. A variation in the spin orbital is completely equivalent to disturbing the charge configuration of the many electron system, and the moment you move a part of the charge, you have got an atomic core and you move some of the charge, displace it, the rest of the charge is not going to remain insensitive to this. The rest of the charge will respond to it, because there is a 1 over Rij term, right. So, the rest of the charge will readjust immediately, right. Now, our approximation in the present context is that we ignore this. Okay. It is not a bad approximation. As you will see, this is what is called as the frozen orbital approximation, and it is at the very heart of the Hartree-Fock theory. What it means is that when you vary one orbital, it is pretended that the rest of the charge distribution is frozen. So, this is called as the frozen orbital approximation, and you vary only one orbital at a time. So, let us say you vary one orbital, namely the kth orbital, it does not matter any. So, from 1 through n you pick the kth one, and we will seek variation only in the kth orbital, other orbitals remain fixed. This goes at the very heart of Hartree-Fock theory. This is not a bad approximation, but since it is an approximation, you do need to go, physicists, atomic physicists have to go beyond it, and then there are theories which are developed to go beyond the Hartree-Fock, and we can talk about it only if we survive the Hartree-Fock itself. Okay? So, we will get to that. So, this is the frozen orbital approximation, and it is also called as an independent particle approximation, okay, because the Slater determinant is written as a product of one particle functions. What it really amounts to is that you are ignoring something, right, or what you are ignoring is precisely what gives you the definition of a Coulomb correlation. Okay. Coulomb correlation by definition is what is left out of the Hartree-Fock. Okay. So, good way of defining Coulomb correlation is the whatever correlation is there in the many electron system which the Hartree-Fock does not take into account is the Coulomb correlation. So, correlations are of two kinds. You have Coulomb correlations and exchange correlations. Now, exchange correlations are indeed taken into account in the Hartree-Fock formalism. How and why? Because they come from the Fermi-Dirac statistics. Okay. So, that correlation is taken into account because what we have done is we have worked with the Slater determinants, which are proper antisymmetric wave functions. Okay. So, they already take into account the Pauli exclusion principle, they already take into account the Fermi-Dirac statistics. Okay. These are the exchange correlations, and these correlations are already taken into account in the Hartree-Fock formalism. In the original formalism, by the way, which was due to Hartree, even the exchange correlations were excluded, and then in the Hartree-Fock they have been properly taken into account. So, I did not take you to those two steps, Hartree's method followed by Hartree-Fock, instead I have done Hartree-Fock straight away. Okay. But Hartree's is a subset of Hartree-Fock in which you do not take into account the exchange interaction. So, if you throw the exchange interaction, do not worry about the exchange interaction. Okay, the Pauli exclusion principle, the Fermi-Dirac statistics do not demand that your wave function must be antisymmetric. If you do not make that demand and carry out the same procedure, you have got Hartree's method, which was the original historical method. So, exchange correlations are included, but Coulomb correlations are excluded in the Hartree-Fock. So, these are the two kinds of correlations. Exchange correlations are also called as Fermi correlations or Fermi-Dirac correlations. This is just a matter of terminology, and you can see why these terms are completely equivalent to each other, because it comes from Fermi-Dirac statistics. These are also called as statistical correlations because they come from the Fermi-Dirac statistics, right. And to handle Coulomb correlations, you must go beyond the Hartree-Fock, and there are methods which are very well developed. These are many body, this is formal many body theory. Even Hartree-Fock is a many body theory in a certain sense. But when atomic physicists talk about many body theories, they usually talk about going beyond the Hartree-Fock. Okay. And you use quantum field theoretical methods, you use second quantization method or configuration interactions, you do things like multi-configurational Hartree-Fock, and we will talk about something if and when we survive the Hartree-Fock. Okay. So, we will get to that a little later, but let me just, this was just to let you know that what we are doing is the frozen orbital approximation, which is the core of the Hartree-Fock approximation. It leaves out something. What is left out is the Coulomb correlation, what is included is the exchange or the statistical correlation, and this is what our problem boils down to, which is to seek a variation in this function subject to these constraints. So, this is the equation that we have to solve, right, of which let us handle this piece, because there is plenty to work with. You have to work with this piece, you have to seek a variation in this, you have to seek a variation in this, right. So, there is plenty to work with, we will do it term by term. So, we will first focus our attention on this piece, and this piece is a sum of the 1 electron integrals and the 2 electron integrals, which contain the Coulomb integrals and the exchange integrals with the parallel spin restriction expressed by the Kronecker delta, right. So, let us focus our attention on just this term, and in the frozen orbital approximation we will vary only the kth orbital. So, all other orbitals will not change, so variation in those will vanish. Okay. You understand the frozen orbital approximation now? So, this is the only term which you have to take into account, and in this let us just look at the first 1 electron integrals. Okay. We will also work with the Coulomb and then with the exchange, but let us work with just the 1 electron integrals coming from the 1 electron Hamiltonian H1 and seek a variation in the kth orbital alone. So, only the alpha, the kth one, the I is going from 1 through n, and you have so many n quantum states, of which only the kth one is going to be varied. So, you will have a variation only in the kth orbital, delta uk star coming from here, right. That is the only one that will contribute, and then there will also be a term coming from alpha I equal to k. So, there will be a delta uk variation term here, and then there is a plus dot 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 over here and here, which come from the 2 electron Coulomb and exchange terms. So, these are the terms that we have to learn to handle. Okay. So, the problem is very well posed, and we will continue from here in the next class. What we have done is to expressed our, we have posed our problem as a problem in variational calculus, that we seek an extremum of the expectation value of the Hamiltonian in the n electron state subject to certain constraints, and this is expressed in terms of the 1 electron integrals and the 2 electron Coulomb and exchange integrals, and then this is to be varied within the framework or of the 1 electron frozen orbital approximation, which excludes the Coulomb correlations, but the exchange correlations are in fact taken into account, subject to the constraints which have now been plugged in, and we will continue from this point. But in the next class I will be happy to take some questions. So, I want you to grasp the methodology, okay, the technique, the physics that is going into it. Okay, the mathematics is not difficult, it is undergraduate variational calculus. So, the problem is not mathematics at all. The mathematics that we have used in our entire analysis of the Hartree-Fock, or whether it was relativistic quantum mechanics or in any of the topics that we dealt with, the mathematics is really very easy. There is nothing beyond second order differential equation. Okay, there is nothing beyond matrix algebra, finding inverse of a matrix and that kind of thing, right. So, they are very simple mathematical tools that you are using. The essential idea is to follow the development of the subject, and if you follow this development, the mathematics can be very easily plugged in. Questions?
Yes sir, so the variation is only the k orbital So when you do it to the conjugate UK star, then FR, then why have you considered UK? Shouldn't you consider all the orbitals for UK?
No, all the other orbitals are not going to change.
Variation we are seeing right now only in the conjugate, and by
No, it's only one variation for I is only varying, right? So it's not I and J. So if both will be same, indices should be same.
This is just the integral over I. This is a summation over I going from 1 through n. You do it term by term. So anything in which alpha I is not equal to k, variation in that will simply vanish. So that is not going to contribute anything to this. Okay, it will vanish because of the approximation that we have made, which is the frozen orbital approximation. So this is a consequence of the frozen orbital approximation. There are very exciting many body theories which go beyond the Hartree-Fock. There is a random phase approximation, for example, there is a multi-configurational Hartree-Fock, then you do the relativistic variants of this. So there is a lot to talk about, but then let us get there. We will cross the bridge when we get there. Any other question? Okay, so thank you for now.